Okay, good morning, guys. Today is day 7. Sorry for the little bit of late posting. Okay, let's get at it because we want the day to start. The earlier we start, the more you guys have time to do your work. Someone just came, 2 people. Okay, so let's start with the land acknowledgement. We acknowledge we are hosting the lands in Mississauga of the Anishinaabe and the Haudenosaunee Confederacy and the Wendat. We also recognize the enduring presence of all nations, all First Nations, Métis, and Inuit people. So today is Wednesday, July 12th, day 7. We're already now on Unit 3. In 7 days, we're already in Unit 3. Unit 2, the quadratic test is due today. You guys got to work on it. One thing that we can't do is I have 42 students here. We have 12 sections of grade 11 functions. And we all are coordinating and doing the same thing between all 12 teachers. We have to have the same deadline, right? So all of us teachers have the same deadline, right? So I can't extend the deadline because it wouldn't be fair, because first of all, there's people who hand it in on time. And it's like, it has to be the same, because I have to, at some point give you guys the answers, and I can't give out the answers if I gave extensions right away, right? So all of the teachers, the 12 teachers teaching, all have the same due dates and all have the same tests and quizzes and exam. So we have to coordinate to make sure everything's done at the same time. If you forget, or I missed time, I forgot the time, I didn't realize the time, I can't help you, right? It has to be some kind of something where you have to give the note to the VP or something to prove that why you need the extension. Otherwise, I can't give you the extension. Mind you, one test is not going to make you fail. So you know that, right? One test will make you fail, right? We still have a collimating. This collimating is worth 30%, right? The collimating is there's 2 parts, is worth 30%. That's more than any test. So understand, you can't bend over backwards for one simple test or one small quiz extension when there's going to be bigger things down the road that would help you, which you cannot. You have to submit. Okay, so let's not be sending me emails about, can I have an extension? Can I have an extension? It is what it is. I got to keep it the same. I can't break it. Okay, so please, you sign up for this course. It is what it is. Like in 7 days, we're already starting in Unit 3. Like Unit 3 would have been in 2.5 months would have been, maybe would have ended Unit 2 during school year, right? In 7 days, we're already in Unit 3. So it is what it is. If you're thinking it's too much to handle, then maybe you have to think about dropping. I'm not encouraging you to do that, because I'm telling you, you can still pass. And mind you, this is not grade 12, right? So grade 12 is obviously the most important one, because your marks, grade 12 marks do count, right, for university. Grade 11 marks, not so much. But you still want to do well. You still want to, know the stuff. So you're ready for grade 12, okay? So that being said, let's get into what we're going to do today is exponential functions. I think, was this a little bit of a review? I'm not sure. I don't know. No, you didn't do this in grade 10. I don't think so. So you're dealing with exponents, growth, and decay. Okay. So let's go to content. Let me look at it as a student first. That way I know I can see what you guys can see. So I'll go to content. Okay, there's a lot of stuff here. I have to maybe organize the list a little bit better. Okay, so we're going to deal with exponential growth, and then we have exponential decay, and then we have, I don't think this is for today. I think it's just exponential growth and exponential decay. So lesson 1, lesson 2, these ones, graphing properties and transformations, that's the next day. So let's deal with exponential decay. Unfortunately, there is no video for this. So I will create the video as we go. That's what we're gonna do. So let us do this. I mean, obviously there's a lesson here. I'm gonna go through the lesson and we'll do like that. So let me make this, maximize the screen. Okay, so what we're talking about today is exponential decay. Let me see if I can zoom this. You guys need to be able to see it more. So many things on my screen here. Okay. I think that's better. Go a little bit more. Okay, that's better. Okay, so exponential growth, right? We're dealing with exponents as the variable. Okay. When we're dealing with ordinary functions, the exponent is not the variable, right? So in this case, and the way it grows exponentially, because if, for example, looking at this one, if I had 2 to the power of 1, first of all, 2 to the power of 0 is 1, right? 2 to the power of 1 is 2, 2 to the power of 2 is 4, and you can see how it starts growing exponentially. When I have each x value, it goes up. Like, for example, let's say at 0, my y is 1. At, I think these are, let's see, 1, 2, 3, 4. So these are every 2. So at 0, I'm at 1. When x is 2, I'm at 4. When x is 4, I'm at 16, right? So it grows really fast as I move along the x. Okay, so here we're talking about population of bacteria. So let's look at it. Type of bacteria grows so that it triples in number every day. On the day we begin observation, the bacteria has a population of 100. So on day 0, it's 100. And you can see it's tripling every single day. So x is my independent variable, which would be the days, 0, 1, 2, 3, 4. And y is my dependent, is dependent on my x. So whatever day my x is, that will determine my population, right? So you can see day 5, I'm at 24,000. That's just after 5 days. Okay. Now, what we're doing here, I don't know if you guys remember for, excuse me. I didn't drink my coffee this morning, so. I don't know if you guys remember in grade 10 when we talked about differences, first difference, second difference, okay? That first difference is second difference is something to basically let you know there's a pattern, and the pattern will determine if it's a linear relationship, if it's a quadratic relationship, or in this case, if it's an exponential relationship, okay? So here it's showing that it's an exponential relationship because I have to do my first difference. In between each difference, it's increasing by 3, okay? So it's growing exponentially by a multiple. And that's what we say it's tripling every 3 days, right? Every 3 days it's tripling. And this shows you that that's what's happening. So this is the definition right there. If a finite difference of a set data increased by a constant multiple, it's an exponential difference, right? The multiple is constant, the multiple of 3. If you remember in, I don't know, in grade 9, we might have talked about linear relations. When you got the first difference, right, it was the same value. So you see how my first difference here is 200? After each one, if it's linear, it'll always be 200, right? That's when we were talking about linear relations. So I'm just saying how first differences come back into grade 11. But now we're looking at exponential relation, okay? So graphing the population, basically your independent is down at the bottom here is your X value. So 1, 2, 3, 4, 5 days. And on the side is your dependent. It's dependent on the days, and it's the population. So you can see it exponentially grows. Okay. So now you can write an equation for this, right? You can write an equation to model this growth. And we're not going to go, we don't have to really go through the theory, but we do know the relationship between days and total population is easy to see when we look at a number of times the population has been tripled, right? So you can see here, we start off 100, and you can put it all the way down. If you can break it into a formula. The exponent 1 is my day. So you can see day 1, because we're saying, remember, the variable is the exponent. So 3 to the power of 1 gives you 300, and 3 to the power of 2, that means 2 days. 3 to the power of 3, that means 4 days. 3 to the power of 4, that means it's 4 days, my bad. And you can see. So by looking at this, you can actually figure out what is the formula, right? Here's the formula right there. The formula is 100 bracket 3 to the power of X. Now we need to understand what are these things, right? 100 is your initial value, the initial population, right? And 3 is the tripling each day, and then X is the number of days, which, you know, whatever days it is, that will be your population if you plug it in there. Okay, that's just a very basic beginning of exponential. So based on what we see here, what we created from this population, this formula, you have a general formula you can look at now. Here's your general formula. Your general formula, looking at it like this. Oh, maybe I can start writing on the screen. Right? So your general formula is y is equal to a bracket b to the power of x bracket. Okay, a is your initial population, initial amount, we can say. I'm not even gonna say population, it could be amount, because maybe we're talking about money, right? So it's the initial amount. Sometimes this doesn't work. Okay. I'm going to say initial amount, and B is your growth factor, okay? And X is the number of times increased, number of times A increased. Number, I want to say number of times. Okay. Okay, so just meditate on that, right? So you can see here, growth factor is always greater than 1. When we grow, it has to be greater than 1, right? So if I say I doubled every 2 days, it would be what? 2, right? Okay, someone says they have a question. What's your question? Zane, what's your question? Did I miss it? The question is X. Where is that? Where did you see that? I need you to, you know what? I think I need you to speak because it's hard for me to look at these when you start typing in the text numbers, it's hard for me to understand. Can you use your mic?
Hello?
Yeah, hi.
Yeah, so for question 1, for the unit 3 quiz number 1, it says x to the power of 12, and then in brackets it says 0.25 like above it, but I don't know if that's 0.25 or
Okay, I have to go take a look at it. I don't know offhand right now. Okay.
okay.
Yeah. Okay, so so some people are going ahead on to the exponent quiz, but basically this is what we're looking at, right? So now the key that I feel that people get confused with is this part here. I'm highlighting it. So X is the number of times A has increased, okay? So, but X can be broken down by the total time, and then as the numerator, and your denominator, time it takes for one growth period, okay? In this question here, we're just saying days, okay? The whole thing is a day, but you may have to do another type of break it down further depending on the question. So we'll have to look at an example, okay? So let's scroll down to the next. So here is just graphing an exponential, you're just showing an exponential, what do you call it, growth graph, okay? And it's showing you how the change in X, for every change in X, you can see how your Y is just growing, right? Y now is going to 8, it was 4, then it was 2, then it was 1. Every time I change by 1, okay? So here's another example. Your brother tells you a secret. You see no harm in telling your friends. After this second passing of the secret, 4 people know the secret, your brother and you and 2 friends. If each of these friends now tells 2 people after the third passing of the secret, 8 people will know. If this pattern of spreading the secret continues, how many people will know the secret after 10 such passings? Well, what's your initial amount? What was the initial? Only 1 person knew the secret. Okay. And then what was the growth rate? It's basically tells two new people. Okay. So basically your growth rate is 2, because every time you tell 2 people, it's growing by 2, by a factor of 2. And then X is the passing. the time that you want to start looking at, like how many people know. So we can say 10 is your passing. So basically when you look at that, after 10 passings of, I guess 10 passings means spreading the rumor 10 times by 2 people, spreading it to other 2 new people, you're gonna have 1,024 people know the secret. Isn't that crazy? You start off with 1 person, but 1 person told 2 people, and then each person tells 2 other new people, and it just keeps growing. And before you know it, after 10 passings of that secret, you got 1,024 people. See how rumors spread? It's crazy, right? Now that's how many people know the secret after only 1 person knew, but then she told 2 people, and then those 2 people told 2 other people, and those 2 people told 2 other new people. It just keeps going. That's exponential growth. Okay, that's how things spread like wildfire. Okay, here's another one. An insect colony has a current population of 50 insects. Its population doubles every 3 days. So what is the population after 12 days? Okay, so now this is the one where you have to look at the exponent carefully. It says it doubles every 3 days. So your X can be 3 because that's not what we're saying here. It's every 3 days. So, and the thing is that it's asking for the population after 12 days. So you would have to figure this out in a way that, going back to the formula, what's the total time? In this case, we're looking at 12 days. And then in the bottom, it says time it takes for 1 growth period. 1 growth period in this is 3 days. So after 3 days, it doubles. So, but I'm looking at my total time. So my total time by the growth rate, let me use a better term, the time it takes to grow in 1 period. So 12 days divided by the time it takes to grow in 1 period is just 3 days. So my X is 4. So that's basically what I put in there. And I calculate my insect colony to be after 12 days, it's going to be 800 insects. Okay. So we're not going to touch into this log. We didn't do log yet. Log is more of grade 12. So if I start talking about logs, it's going to confuse you guys. That's a grade 12 thing. So if you're taking grade 12 advanced functions next year, you're going to learn about log. So I'm going to skip that a little bit. So if exponential growth is given as a percentage, sometimes they don't just tell you it's doubled or it's tripled. Sometimes they just tell you it's a percentage. It grew by 50%. It grew by 73%. Okay, so now you have to use this formula. And with this formula, again, A is your initial amount. Now, and then X is the number of times it has increased. A has increased, right? So, but what's different is inside here. So R is the growth rate as given as a percentage. So if I say something has grown 75%, I have to rewrite it as a decimal in here. So 1 plus 0.75, okay, gives me my growth rate. And that's what I use to do my calculation. So okay, let's look at examples, right? Here's an example. 2005, there were 285 Pittsburgh Penguin fans in Oakville. The number of Penguin fans increased by 75%. After year 2005, that's when Crosby was drafted. How many Crosby fans are now in Oakville in 2014? Okay, so we're looking at your initial amount is 285. My growth rate as a percent is 75%, but we have to write it as a decimal here. So when you write it as a decimal, it's 0.75. Now, when you go back into the formula, it's going to be 1 plus 0.75 equals to 1.75. And your exponent X, it is what it is. It's there, it's unknown, but we do know we want to figure out how many Crosby fans are there in 2014. If I go from 2005 to 2014, that's 9 years, right? So 9 years. So I'm going to have my variable of X as 9. And then when you do that, you calculate it. So in 2014, I have basically, because you can't have a decimal person. So I have about 43,872 people of fans. Okay, you have to round up because you can't have a decimal of a person. It doesn't work, right? Okay, so that's the end, looks like, of exponential growth. So let's go on to the next one, exponential decay. It's not that much difficult. Sure, it's just basically the same, but we're looking at decay. Okay, so this is what we're looking at. So you can see it's coming down this way. Now, if you look at inside the bracket inside here, you can see it's a fraction. So what you have to know with exponential decay, you have a fraction inside this bracket, a fraction or a decimal. In both cases, it's less than 1. Because in order to have a decay, your growth factor, which in this case is not called a growth factor, it's called a decay factor, has to be something less than 1. Because I'm decaying by a fraction, so it has to be a fraction. It can't be a whole number, right? A whole number would be 2, which I'll be doubling, or 3, which I'll be tripling. So if I'm shrinking something, I got to multiply by a fraction. Okay, that's why you see a fraction there, or a decimal. So like we say here, same formula doesn't change for exponential decay. The only thing is we're looking at a decimal or a fraction between 0 and 1, okay? And X is the number of times it takes to decrease, okay? That's what we're looking at there. So there you go. Total time, X can be broken down to total time over time for one decay period. Okay. So let's get into an example. This is where maybe in chemistry you talked about this. You might have talked about half-life. In chemistry, you might have did some half-life. I don't know if you guys would have took chemistry. You guys are taking grade 11 functions, but I'm not sure if you guys are in grade 10, going to grade 11, or just maybe doing it from grade 11 because you missed it last year, but whatever. If you took grade 11 grade 11 chemistry, you probably would have did half-life calculations, right? So here's an example. Nuclear power plant uses uranium-239 as a power source. So uranium-239 has a half-life of about 2 years, okay? So what does that mean? Every 2 years, it shrinks by a half, okay? Every 2 years, it shrinks by a half. So year 1, I have 1,000 milligrams sample. And then the question is, complete a chart of the amount of 1,000 milligram sample that will be left after 10 years. So start off with year 0, and then after year 2, 500, year 4, 250, and you can see it's going down by a half. Okay, so after 10 years, that would have been 5 periods of half-life. That means it would have went down by half about 5 times. Now we're left with 31.25 milligrams. And now we're just showing you how to graph it. Starting off with 1,000 at year 0, then at year 2, I go down to 500, and then year 4, I go down to 250, and so on. And you can see it's a rapid drop, and then it gets really, really, really small, gradual at the bottom. So now it's saying write an equation. If I'm writing the equation, my initial amount is 1,000, right? So when I go back down here, I'm going to have y is equal to 1,000 bracket. My half-life is my half-life, so it's always going to be a half. And then x is my exponent. Okay. Now, now it says here, how much remains after 25 years? Okay. So x, you have to figure out what that exponent is now, because x is going to equal to what? The total time, which you're given, the total time is 25, divided by the time it takes to go through one cycle of decay. So it takes 2 years to go through one cycle of decay. So it takes 2 years for it to divide by half. So I need to put 25 divided by 2. That's part of my exponent, and then my exponent is going to be 12.5. Okay. So that is what I use as the time to figure out my the amount after 25 years. You can see it's like less than 1 milligrams. Okay, here's another example of half-life. Okay, it says here, find the amount of 50 milligrams after 35 years. Well, my decay is already going to be a half, we know. I started off at 50 milligrams. Now my x, I have to figure out what that is. All right, it says 35 years. Okay, remember, it's going to be total time over the time it takes for one half-life, right? I want to scroll back up because I want you to understand that. It's right here. X is equal to total time divided by the time for one decay period. Okay, so the question will depend, that will depend on the question. In this question here, we said one decay period was 2 years. Okay, and this question here, we're saying one decay period is 24 years. So I'm going to have to divide my total time of 35 divided by 24. Okay, and that will help me. That will give me my answer for my exponent. And over here, you can leave your exponent as a fraction, right? Because maybe I suggest, if you want to get an accurate answer, I would leave my exponent as a fraction and then use that as my exponent that I apply on the half. If you put that, if you divide this out by 24, you're going to get 1 point something, 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 something. And then when you use that exponent of 1 point something, something, your rounding may mess up your answer. That's why if you keep it as a fraction, there's no rounding. Okay, so you get an accurate answer of this 18.2. Okay, so 18.2 milligrams after 35 years. Okay, now just like in growth, we may have percentage where we want to look at decay, right? So if something has gone down by 75%, then we can use it in this formula, okay? Where 1 is what we have, but then R is the percentage how much it went down by. So it'll be 1 minus the percentage it went down by, and that will give you your growth, your decay factor. Not decay rate, decay factor. Decay rate, when we say rate, we're saying percentage. Okay, rate means percentage. Just think about that. When they say interest rate at the bank, they say interest rate. So that's a percentage. Anytime you say rate, it's a percentage. What is the rate of you getting this done? 99%. Okay, so, but when we say factor, it's not a percentage, right? Over here, we said factor. We'll go back to the beginning. We said here, decay factor. And decay factor is the actual number that's not a percentage. So in this case, we say the decay factor is a half because it's getting smaller by a half. When we said decay, when we said growth rate was 2, that means it was doubling by 2. Okay, but here we're talking about rates. So we plug in the rate in as a percent, as a decimal, and then you figure out your answer you need to find out. So here's an example of using it as rate. You buy a new car. Car costs $24,000. The value of the car decreases by 16% every year. How much will the car be worth after 8 years? So it says it decreased every year, okay, by 16%. So you know it's going to be 8. And let me actually write this up on the screen here. So I think, oops, does this work? Come on. So let me use a different color. No, I won't use that color. Use that color. So my exponent, x, is actually equal to, what is it? Number of, I got a brain fart for a sec. I can't remember. Oh, total time. Okay, my bad. Total time. Okay, and at the bottom, it is time for one. I'm trying to find the right word. Time for one period of decay, right? It could have been total time. If I was talking about growth rates, it would have been total time divided by time for one period of growth. But in this case, we're talking about decay because we're talking about decay of decrease of value of the car. So we're talking about that. So now the reason why I did that, because you want to know what your x is going to be. In this case, the total time that we're dealing with is 8, and the time for one period of decay. What's the time for one period of decay? And everything is all in years. The time for one period of decay is, it says here, every year. That means it's 1 year. Okay. If we're looking at what the units are, this is year, and then this is year. I'm kind of breaking that down, but 8/1 is just 8. So that is how, my bad. Let me just, that is how, oh, maybe, you know what? Let me just fix that. That is how we get 8, okay? So I hopefully you guys can remember that, because sometimes how come it's just the number there and sometimes it's like a fraction? Because there is a fraction there. 8/1 is a fraction. But again, x is made up of the total time divided by the time it takes to do one thing. Either the time it takes to do one decay or time it takes to do one growth, okay? In this case, one decay is 16%. Takes every year, it goes down by 16%. That means it's every one time, every year, it goes down, okay? So that's how I got that. So after 8 years, the car is worth about $5,949, so roughly $6,000, okay? And you look at that. This is why they say car is not an investment. You bought it at $24,000. 8 years later, the car is worth this much. So you kind of, you save up for 24,000, 8 years later, the money is worth less. The car is worth less. So that's why they say cars are not an investment, is just something that you use that will, it's just like your car is like your laptop or like your phone. And think about your phone, after 2 years, you want a new phone, right? And that phone is worth less if you go to the store to buy that same phone, right? That's just how your car works, same way. Okay, here's the next example. This person here is taking Advil, and an adult takes 400 milligrams of Advil. Each hour, the amount of Advil in the adult system decreases by 29%. Okay, goes down by 29%. So, and we're saying each hour, right? So again, it says here, let me do this. It says here, how many Advils would be left after 4 hours? So my X is equal to total time divided by time for 1 period of, I'm going to say decay, right? So my total time, my X is going to be, my total time is 4. And then it's saying it goes down every hour. So we say 4 hours for total time, and then it's 1 hour for the decay. So the answer is going for my X is going to be 4/1. It's just going to be 4. Okay, so that's how I get that. Okay. Let's clear that. So after 4 hours, I'll be left with that much in my system. Here's another one. See, now here's a little bit tricky because we're talking about logs. I don't want to get into logs. Logs is how you solve for the exponent, okay? In grade 12, which I teach grade 12 advanced functions during day school at my school, you use logs to figure out what the exponent is, okay? After you, like, for example, I tell you what the future is, I tell you what the present is, but how much time it took, right? So you need to use logs in order to determine that, but we're not gonna go through logs, so that's a grade 12 course, okay? Okay, so now we're going through just basically review of using exponents. Remember, when you see an exponent like this, b to the power of a negative exponent, it's the same thing as writing it like this, okay? So here you want to, be able to know how to do this, right? So we know you're adding all the exponents. So if I'm adding this one here for this, if I'm doing A, I have -2 plus -3 plus 4. So -2 plus -3, that's -5, and plus 4, I'm left with -1. So that's my answer. So when it says this, it may tell you there's only positive exponents. That means I can't have a negative up there. It has to be written like this, okay? That's what it means. You can't have a negative exponent, so that means you have to write it like almost like a fraction if there is a negative, okay? So you can see here, that's how they got that answer. And this here, A3, a to the power of 3, b to the power of -5. Well, we don't want it. We don't want any negative exponents. So you're gonna have to write it like this, okay? Means the same thing. Same thing with this when we go through this. Means the same thing. Well, this is a little bit different because you can see here, let me write on the screen here. This applies, you multiply each exponent. So even the 2 has an exponent, is next to 1 to the power of 1 by the outside exponent. So I got that, I got that, and I got that. So when I rewrite it, 2 to the power of -3, which is 2 to the power of 3 as the denominator, and then u to the power of -9, u to the power of 9 as a denominator, and then, so that's what you write, okay? And then also too, you got 2 to the power of 3, you can rewrite that to 8, right? 2 times 2 times 2 is 8. Okay. And now you have stuff like this. More exponents you have to remember how to do, okay? So here is an example, right? You have A over B, bracket to the power of negative n. Well, basically what negative n does, it reverses everything, right? So the B becomes the denominator, and then the B becomes the numerator, and the A becomes the denominator, right? That's all you're doing here, right? So here it becomes, remember, we don't want any negative exponents. If that's the case, then I'm going to bring it down like this. 3 over 1 to the power of 1, which is just 3, right? Over here, I reverse it, negative 8 over 27, and then you apply the exponent on the inside. So it's going to be negative 8 to the power of 2 and 27 to the power of 2. You got 64 and then 729. Okay, so that looks like it's it for that lesson. These ones are for tomorrow. So I believe I got us. Ooh, did I not put in? Oh, here they are. Okay, so I'm gonna move this. Let me fix this. This is not. As we're here, I'm gonna fix it so you can see it as I fix this. Because I'm gonna put the worksheets there for you. Oh, no, that's not the right one. That's functions exponential. Exponential. Shoot, the lessons are not, the worksheets are not there. Okay, I'm going to get the worksheets. For some reason, I thought they were there. Okay, so the worksheets for exponents and growth and decay, I'm going to put them there. And again, what you probably should focus on, to be honest, is the test that is due today. Okay, you got to get that in by before midnight. And then there's a quiz today. So, and again, the quizzes, you get two chances. I'm going to post the worksheets. Don't spend forever time doing worksheets. Maybe do 1 or 2 and then move on if you get it. Because the whole idea is you want to, like, just, how you say, don't spend too much time. Prioritize your test to get that done today, okay? I see 32 people submitted it, or not even. I don't even think I've seen 32 people submitted it. But I need more of you guys to submit before the deadline, okay? So I'm gonna stop sharing my screen. Hopefully you guys are on track and working hard. I appreciate you guys waking up, the 23 of you guys coming in at 9 o'clock in the morning to start your day early. It's better to start your day early with this versus when I had the meetings last week at 10:30, but now we're back to regular time. I know some teachers do it at 11. I still think that's too late. Because you guys, the earlier you guys wake up, the better for you guys to at least start your day and then learn the lesson and have time. Okay, so I'm going to end the meeting now, and I will see you tomorrow at the same time, 9 o'clock. Okay, take care, guys. Bye.